We've now reached the halfway point in this 60-lecture series. How appropriate, then, to start looking at the largest structures in the universe, galaxies, which are vast collections of stars. This lecture is organized into two closely related parts. First, I'm going to review the history of the great debate on the nature of the nebula. This was a controversy that culminated with the discoveries of Edwin Hubble in the 1920s. Hubble's research, as much as any scientific discoveries of the 20th century, have changed our view of ourselves and our place in the cosmos. Then I'm going to survey the magnificent variety and the surprising distribution of galaxies, the way they're distributed throughout the universe. And while reviewing the galaxies, I'm also going to look at several of the techniques that are used to study these distant objects. The most obvious objects in the heavens are stars. Countless millions and billions of stars that are systematized on the Hertzsprung-Russell diagram. On the Hertzsprung-Russell diagram, we see main sequence stars. These are stars that burn hydrogen, from the small, cool brown dwarfs up to the supergiant stars, the most energy-emitting stars in the universe that are super hot as well. And we see on the Hertzsprung-Russell diagram other kinds of stars as well. For example, the red giant stars, large stars that are emitting large amounts of energy but are relatively cool on their surface, just a few thousand degrees. And then other stars, the white dwarfs, intensely hot stars, tens of thousands of degrees at their surface, and yet not emitting very much energy at all because they're so small, the white dwarf stars. We've also seen that stars have various fates. Many stars larger than the sun explode, and when they explode, they provide raw material for the next generation of stars. Well, if you think about that, it leads you to an inevitable conclusion. All stars depend on the presence of prior groups of stars to seed them, to provide the raw materials for those stars. So stars must occur in groups. As we look into the sky with even modest-sized telescopes, you can see the hazy band of the Milky Way, and you see that it's actually composed of countless stars. There are also other objects that appear as fuzzy masses. These are called nebula. And nebula were enigmatic objects. With telescopes in 1900, no one could be sure. And there was a great debate going on. Some astronomers thought nebula were merely dust clouds. That is, clouds of debris that were too small to be resolved by any telescope. And they also were fairly close by within our own galaxy. But other astronomers thought that nebulae were actually distant clusters of stars so far away that no telescope could resolve those individual stars. This controversy came into sharp focus on April 26, 1920, when rival astronomers, the American Harlow Shapley, who was born in 1885, died in 1972, and his fellow countryman Heber D. Curtis, who was born in 1872 and died in 1942, engaged in a public debate at the National Academy of Sciences in Washington, D.C. They debated the origin of nebula. The younger Shapley had come into great prominence by discovering that the Milky Way galaxy was vastly larger than anyone had previously thought. In fact, he showed it was more than 100,000 light years across. Well, given that immense size, maybe a factor of 10 larger than any previous estimates, it turns out that Shapley couldn't imagine that there were much more distant objects that existed. It's sort of ironic that Shapley, who greatly increased the size of the known universe, could not really accept how much larger it really was. Curtis, on the other hand, argued that nebula are much more distant galaxies like our own, that is, clusters of stars. And he looked in his telescopes and he saw spiral shapes that were reminiscent of what people thought the Milky Way might actually look like from a distance. Curtis was the more senior of the two, and apparently the more eloquent of the two as well. And most observers thought that he won that debate at the National Academy of Sciences. But you know, debaters don't settle scientific controversies. Facts and data do. And so, as so often happens in science, it was a new instrument, an improved instrument, that led to the conclusions about what galaxies really were. Both Shapley's and Curtis's hypotheses made specific predictions just like any good scientific hypothesis would. To Shapley, nebulae were clouds of dust and gas, so even the most powerful telescope wouldn't be able to resolve any specific structures in those nebulae. But to Curtis, nebula were clusters of stars, so if you had a powerful enough telescope, you should be able to see those stars. Well, a new telescope, a larger telescope, quite literally could resolve this issue. The discovery of the true nature of galaxies was made by the American astronomer Edwin Hubble in 1924. Hubble was a remarkable scientist who excelled in many different fields. He was born in 1889. He was educated in the Midwest. He went to college at the University of Chicago, where he was a star athlete and an honor student as well. For a time, he thought of becoming a professional heavyweight boxer. He was apparently an excellent boxer, but he decided instead to go to grad school. He won a Rhodes Scholarship to Oxford. He studied law at Oxford, of all things, because he was fascinated by the British legal system. But while at Oxford, he also became a star track athlete, and it's said that he also boxed in an exhibition match the national champion of France. Quite a fellow, that Hubble. Well, Hubble came back to the United States. He opened a law practice in Louisville, Kentucky, but in less than a year, he decided that law wasn't really for him. He wanted to be an astronomer. So he went back to the University of Chicago for a PhD in astronomy. World War I intervened, and Hubble enlisted as a private in 1917, but his excellence was quickly seen, and he rose rapidly in the ranks, all the way to major by the end of the war. At the end of the war, in 1919, he joined the Carnegie Institution of Washington and went to their new telescope facility at Mount Wilson near Los Angeles, California. Now, in order to resolve that nebular debate, Hubble focused on an unusual type of star called Cepheid variables. These are stars that get brighter and dimmer and brighter again in periods ranging from a few hours to several weeks. Now, these are giant stars. They're 3 times or more the size of the sun that have just started the helium burning process in kind of a fitful sort of way. You start helium burning and the star balloons out, but when it balloons out, it gets cooler, and so it starts contracting again because the fusion stops. And then it starts helium burning again, and then it starts cooling down again. So you have a period when the star actually gets larger and smaller, putting out more and less energy over these cycles of a few hours, a few days, or a few weeks. In 1912, astronomer Henrietta Swan Leavitt had discovered a remarkable relationship between the period of a Cepheid variable, that is the time it takes to brighten and dim, and its absolute brightness, how much energy it's putting out. Leavitt was employed as an astronomical computer at the Harvard Astronomical Observatory. Now, computers were people who looked at glass photographs, measured the positions of stars. And this was an incredibly tedious job, one of the very few jobs open to women in science at the time. She was analyzing photographs of the Large Magellanic Cloud. This is a large collection of stars in the southern sky. And it turns out all these stars, because they're in a cluster, are at about the same distance from us. And therefore, the relative brightness of stars in that cluster corresponds to their absolute brightness. That's an important point. What she found was that the brighter stars have longer periods. So here's the trick. Since the absolute brightness of these stars is directly related to their period of brightening and dimming, you can look for variable stars in more distant objects. You can see how long it takes for them to get brighter and dimmer. You can see what their relative brightness is to us, and you can determine their absolute distance from these observations. So by measuring the period, one knows the absolute brightness. By measuring the relative brightness, you therefore know the distance. It's a neat trick in astronomy, and one that's very important in determining distance to various objects that are far away. Well, Harlow Shapley had estimated that Cepheid variable stars in the Milky Way galaxy ranged up to about 300,000 light years away. Now, this was a bit of an overestimation, but still, it showed that the scale of our Milky Way is 100,000 light years or so. Using the Mount Wilson telescope, the Cepheid variable stars in the galaxy M31, known as Andromeda, which is one of the closest, one of the brightest of these galaxies, turned out to be resolvable for the very first time. And Hubble found that M31, Andromeda, was more than 500,000 light years away, far beyond the Milky Way. And M31 was one of the very brightest, one of the largest of these objects in telescopes. So other galaxies must be much farther away than that. Millions, tens of millions, perhaps hundreds of millions of light years away. Hubble had demonstrated that nebulae were in fact vast, gravitationally bound groups of stars, perhaps tens, perhaps hundreds of billions of stars. These objects are called galaxies. Following Hubble's discovery, astronomers began an immediate, intensive search for galaxies, all kinds of galaxies, and that search continues today. So I want to review some of the types of galaxies that are found, some of the great variety, fascinating, beautiful types of galaxies that occur throughout our universe. The Hubble Atlas of the Galaxies, which is published by the Carnegie Institution of Washington, is one place you can go and see many photographs of beautiful galaxies. This is a remarkable book, this Hubble Atlas of Galaxies. Page after page of incredible photographs that show the type, the range of spirals and other sorts of galaxies. And just looking through this to think of each of these as a collection of tens or hundreds of billions of stars, it's remarkable to think about. So I recommend, if you ever get a chance, look at this. It's a 2-volume work. It weighs a lot, but it's well worth the effort if you get a chance. What we find is the galaxies come in many sizes and many shapes. The most familiar are the spiral galaxies, which account for probably 3/4 of all the large galaxies that we know of in the universe. Now, spiral galaxies are characterized by beautiful arms that curve about a bright central core. The Andromeda galaxy, which is M31 that I mentioned before, is a typical example of a large galaxy, a spiral galaxy. It has more than 100 billion stars in that spiral. Seen on edge, spiral galaxies reveal a flat disk and a large central bulge. Most of the stars are in the central bulge, but lots of stars are in the arms too. In our own Milky Way galaxy, it's a typical spiral. And our home is out on one of the arms, about halfway out from the center. So in a sense, we're in the suburbs of the galaxy in a relatively lightly populated area of stars. We'd see far more stars if we were near the center of the galaxy than we do where we are right now. By the way, the Milky Way is that bright band of stars that you see in a clear, dark night. And it's our view of the galactic plane. It's seeing the galaxy on edge. There are large concentrations of dust that obscure that central bulge in our own galaxy. You have to use other wavelengths. For example, if you use microwaves, you can actually get a clear view of the entire galaxy. And recent microwave photographs of our galaxy on edge are spectacular and show a galaxy very much like other spirals on edge. There are many other kinds of bright galaxies as well. Some of them are very uniformly rounded collections of stars that don't have arms. These are called elliptical galaxies. And ellipticals represent about 1/5 of all the known bright galaxies. They often contain hundreds of billions of stars as well. That's really hard to imagine what 100 billion stars is. That's dozens of stars for every man, woman, and child on Earth. And each of those stars could have a planetary system. And each of those planetary systems might hold life. It staggers the mind to think about the scale of the universe. There are also smaller, irregular, and dwarf galaxies. These are relatively faint, but they're remarkably abundant. They still contain billions of stars. They're still thousands of light years across. And they may be the most abundant galaxies in the universe. Now, there are a relatively small number of galaxies that have chaotic shapes. These result from the collisions of two other galaxies. They're gravitationally linking as two galaxies come in contact with each other. But what might surprise you is that even though these galaxies interact, even though they're colliding in a sense, even though they have hundreds of billions of stars each, the chances of any two stars actually hitting each other is almost insignificant because the stars are so widely spaced. So two galaxies can interact gravitationally without ever having a stellar collision. Now, in describing galaxies, distance is one of the most important measurements we can make. And a lot of the effort in modern astronomy is devoted to developing improved methods for determining distances to galaxies. Even the closest galaxies are much, much too far away to measure by parallax, that is, by triangulation. Think of it this way. The Earth swinging side to side in the Sun in its orbit covers a distance, a diameter of about 16 light minutes. It takes 8 minutes for light to get from the sun to the Earth, so the total distance across 6 months apart is about 16 light minutes. But the closest distant galaxy is hundreds of thousands of light years away. And so you just don't get enough of an angle to do triangulation on distant galaxies. You have to have some other method. So the technique Hubble used was the Cepheid variable technique. That is, a star of known brightness, a standard candle. And this method, with improvements, is still used for galaxies up to tens of millions of light years away. The high-resolution photographs from the Hubble Space Telescope are particularly useful in this regard. The Hubble Space Telescope images allow you to resolve Cepheid variable stars in some galaxies that are 50 or 60 million light years away. Now, there are other distinctive kinds of stars, bright stars, including the very brightest red giant stars and what are called the brightest main sequence stars, or supergiant stars. And these stars also can be used as standard candles. You have to assume that the brightest stars that we know of are the same all over the galaxy, but that's a probably pretty good assumption. And that gives you another kind of standard candle to measure distance. We also have standard candles called type 1 supernovae. These are very interesting kinds of supernovae, exploding stars. And let me tell you how this occurs. This is a fascinating story. You have two stars that are orbiting each other in a binary system. Imagine that the larger star is almost large enough to explode as a supernova star, but not quite. But it keeps sucking material up from its companion star. More and more hydrogen and helium gets pulled from the smaller star to the larger one, until all of a sudden you reach that critical mass when the star is just large enough where the temperature and the pressure inside the star gets just high enough, and suddenly the star can go all the way to iron 56. And when it goes to iron 56, remember, the star burns out, it collapses gravitationally and becomes a supernova. But every one of these type 1 supernovae have exactly the same mass, the same energy, so they become a standard candle. And indeed, that standard candle is roughly 50 million times the sun's energy output. Now, a star may burn for billions of years before it becomes one of these exploding supernova stars. And so you might think that the chances of seeing one is almost infinitesimal. And yet remember that every galaxy has tens or hundreds of billions of stars. So actually, it's a fairly common event to see a type 1 supernova in a distant galaxy. Other approximate distance scales rely on things like the size and brightness of entire galaxies. If you have a cluster of galaxies, we can make an assumption about how bright the brightest galaxy is in a cluster, something like Andromeda or the Milky Way, which are large galaxies, and use that as a standard candle itself, the entire galaxy. It requires a lot more assumptions, but still, it's not a bad way to get an approximate distance for something that's billions of light years away. There's an important caveat to all this. We have no way of knowing how much intervening dust there is. If there's no dust, then we get a true measure of the distance to an object, because the brightness we see is the actual apparent brightness of that object. But if there's dust in the way, then an object seems fainter than it really is. And so it will seem farther away than it really is. Now, infrared radiation is not nearly as strongly absorbed by dust as visible light. And so one way of getting around this problem is to measure the brightness of an object both in visible light and in infrared, and seeing the ratio of those two. And that can give you some measure of the quantity of dust, but it's still a very difficult proposition. Well, studies of standard candles have led to yet a different method of determining distance. And this is the redshift method, using the Doppler effect, which we've talked about several times already in this course. Now, the redshift is the change in wavelength. When an object is moving away from you, it spreads out the wavelengths, for example, the wavelengths of light. And so what might be a hydrogen line in its normal position is shifted towards the red end of the spectrum. What Hubble noticed in an astonishing discovery, the transforming discovery of galactic astronomy, was that the more distant object, the more distant the galaxy is, the greater its redshift. He saw a very simple relationship between redshift and distance according to Cepheid variables. So you calibrate the redshift by looking at the shift of hydrogen lines or some other absorption lines. You calibrate the distance by looking at Cepheid variables, at least for stars that are out to 50 million light years or so. And he saw this relationship. For example, you have a galaxy in the Virgo cluster. It's 63 million light years away. It turns out that it's moving away from us at 1,200 kilometers per second. That's not very fast according to light speed. That's only about 1/3% of light speed for a galaxy 63 million light years away. But there's another galaxy, for example, one in the constellation Hydra, that's about 4 billion light years away. And that galaxy is receding at 61,000 kilometers per second. That's almost a fifth of light speed. And this was a relationship that was seen over and over again. The more distant galaxies are moving away much faster. This led to something called Hubble's law, a law that states the velocity of recession of a galaxy is directly proportional to its distance. Well, Hubble's discovery was based on first determining the distance to the galaxy and then measuring redshift. But think about what this means. If you have a relationship between distance and redshift, then all you have to do to measure the distance to a galaxy is to determine the redshift of the galaxy. You don't have to worry about Cepheid variables or standard candles or exploding supernova and things like that. You just measure the galaxy's distance by seeing how much the hydrogen lines are shifted. And that's very easy because every star, every galaxy is sending us photons from hydrogen, so we can see those hydrogen lines even from the most distant galaxies. Now we're going to explore the profound consequences of this idea that more distant objects are moving away from us. It's called universal expansion. The universe is expanding, and that has very great consequences about the origin and the ultimate fate of the universe. But for this point, it just gives us a practical way of measuring distance. Now, as telescopes have become more powerful, the number of known galaxies that we can measure has grown tremendously. The Hubble Space Telescope did a really interesting experiment recently. It focused on a small area of sky that you might call an empty region. What I mean by that is this is a region of sky where there were no stars whatsoever from the Milky Way galaxy. Just a piece of black space, if you will. And any normal telescope looking at that region of space would see nothing. But the Hubble Space Telescope is so powerful, it has such high resolution, that it was able to focus on that small area of space in the northern sky for several days and actually get a very high resolution image of that distant slice of space. What it found is absolutely remarkable. They found not just a few, they found dozens of galaxies. Galaxies that were billions or tens of billions of light years away in what's called a dark field image of the northern sky. And just to make sure that they weren't biasing the results sometime by randomly picking an area that might have had extra galaxies, they did the same thing in the southern hemisphere. They found another piece of dark sky, another piece of sky where there were no known stars. And again, dozens of galaxies that were a billion up to 10 billion light years away. And if you take that small area and you figure out how many galaxies are in it, and then you multiply over the whole vast area of the entire sky, the result is absolutely staggering. The minimum estimate for the number of galaxies is on the order of 50 billion galaxies. And remember, each of those galaxies has tens or hundreds of billions of stars. Carl Sagan is often characterized as saying billions and billions, but indeed, that's what the universe is. There are billions and billions of galaxies, each with billions and billions of stars. It's a staggering thought. A major effort's now underway to map the distribution of these galaxies in 3 dimensions. Now, this effort, of course, is difficult because if you look at the heavens, you see a 2-dimensional surface, and you have to measure that 3rd dimension. You have to measure distance to every galaxy that you see in your telescope. But you can do that now with the redshift of each galaxy, so we can get the proximate distance to each of those galaxies. And so you can start mapping in 3 dimensions the distribution of galaxies throughout the universe. And this has been done now. Every year there are thousands more galaxies that are added to the list. And computer programs generate 3-dimensional models of the universe. And what they found is fascinating. Galaxies are not just randomly distributed. Turns out galaxies are distributed in clusters, local clusters, and more large-scale clusters, and then superclusters of galaxies. And separating those clusters, they're vast voids in which there are very few galaxies indeed. Indeed, there seems to be a large-scale structure to the universe that we never suspected before. Let me tell you about where our own Milky Way galaxy lies, because that's probably our chief interest here. The Milky Way galaxy is part of the local group of galaxies. It's about 30 galaxies. And there are two big ones, the Milky Way at one end of this cluster, if you will, and Andromeda, about 2 million light years away, it turns out now, at the other end. And this local cluster are all gravitationally bound together. The Milky Way and Andromeda are actually very slowly rotating around a common center and sort of herding along these smaller galaxies, including things like the Magellanic Cloud that I talked about earlier. Okay, then there's several other clusters of galaxies that are relatively nearby. By far the largest of these is called the Virgo cluster. It's about 10 million light years across, and it has hundreds of galaxies. Now, the Virgo cluster is about 50 million light years away from us, but it's so massive that this Virgo cluster actually has a gravitational attraction with our local cluster, and our local cluster is being pulled towards the Virgo cluster. So here's one small group of galaxies where we, instead of seeing a red shift, we see a blue shift, because we're moving towards them, wavelengths are being piled up, and so there are actually some galaxies in the heavens that are reasonably far away, a few millions or tens of millions of light years, that have the blue shift. Now, the local group, the Virgo cluster, and several other clusters seem to be part of an even larger gravitationally bound group called the local supercluster of galaxies. That's arranged in a disk about 100 million light years across, sort of in a disk-like arrangement. And the total mass of this collection of galaxies is estimated to be 1,000,000 billion stars. Well, then we have the three-dimensional maps. Our local supercluster then is part of various surfaces and voids in a much vaster dimension that goes outwards to 10 billion light years and more. This is a vast scale. It's hard to imagine how vast our universe really is, and that'll be one of the subjects we talk about in the next lecture, trying to get a scope of this idea of light years, tens of light years, millions of light years, and billions of light years, distances far beyond any imagining. Well, let me summarize this lecture. The mystery of the nebula was solved by Edwin Hubble. Using grand new instruments with high resolving power, he was able to see individual stars in these distant nebulae. Nebulae aren't clouds of dust. They are, in fact, vast collections of stars that are gravitationally bound together. He showed that nebulae, therefore, are galaxies, huge collections of stars that are far beyond our own Milky Way, distributed throughout the universe and giving a scale of the universe which is so much vaster than we could have imagined. There are billions of galaxies. Most of them are spirals. The ones that we can see that are large galaxies also include ellipticals, each of these containing hundreds of billions of stars. And then we have smaller galaxies, the vast number of dwarf galaxies, which litter the universe, and irregular galaxies, galaxies where two other galaxies have collided and gravitationally pulled each other apart into chaotic shapes. Most of these objects are hundreds of millions or billions of light years distance, and most of them are moving away from us at vast speeds. According to Hubble's law, which states that the farther away an object is, the faster it seems to be moving. Now, one of the greatest mysteries in cosmology today is the origin of these gigantic structures. How can you have a structure in the universe that's hundreds of millions of light years across? And for answers to that question, we have to go back to the very beginning of the universe, the Big Bang. And that's the subject of the next lecture.